Boa tarde a todos. Good afternoon. So we are going to start our afternoon session. And let me start by saying that it's really an honor and a pleasure to have Professor Chris Rogers from the University of Cambridge here with us. Chris has been regular in our events and doesn't need introduction given the fact that well, he has done such important work in several areas of probability and math finance. But still, I want to thank him for, once again, taking the opportunity and the time to come here to Brazil to give a talk. And so, Chris, please.
Well, thank you very much, Jorge. And I'd firstly like to thank you for inviting me again, which is very, very kind of you, and congratulate you on the 10th event in this series, of which I've been to a very good number. I don't know if you've ever been invited to a fancy dress party. And you go along, and you turn up, and you find actually it's not a fancy dress party at all. It's a formal dinner. So if you can imagine how it feels to be sitting down to an elegant meal dressed as a tiger, then you can kind of understand how it feels for me, because based on history, I've been expecting this to be a sort of beach conference, whereas actually it turns out to be more a conference.
Chris, in Rio, anything is accepted provided it's within the law.
Well, thank you. I knew that nobody would mind, but I hope you don't you sort of think that this is how I always address an audience. Anyway, so let me just sort of give you a few words about what I'm going to be talking about here. So this is some stuff I've been doing kind of recently, and it's about how we do Bermudan options. How do we... So the title is not pricing Bermudan options, it's not hedging Bermudan options, because we're going to do both. So a Bermudan option, you know, as we all know, is an optimal stopping problem. So to set up some notation, we imagine we've got some Markov process X, and if we stop at time tau, we get a reward, which is a function of the time at which we stop and the state of the Markov process at that time. And we simply want to choose the stopping time bounded above by some finite capital T, a horizon, to maximize the expected reward when we stop. That's what it is. And we all know how to do this. We've taught our students how to do this for many, many years. You find the value function. So you define the value function v at time t in state x to be the best you could do if by time t you haven't yet stopped and you're currently in position x. And then you tell your students the Bellman equation that the value at time t in position x is the better of either the reward you'd get by stopping straight away or the expected value that you'd get by moving one step ahead. And in principle now, if we know the terminal condition, which we do at time capital T, we've got to stop and take the reward at that time, that's it, then by backward induction, we can work back from t plus 1 to t and go all the way down to time naught and discover the entire solution. So this is well-known stuff. But what I'm going to talk about today is how does this work out? Does this work out if the state space of the problem is very high dimensional? So when we look at the steps involved in this Bellman argument, we have to do things like calculate an expectation here. So we're calculating an expectation conditional on the value of x, and this is an integral over a very high-dimensional space. It's an integral over a high-dimensional space of a function that's not going to be available in closed form. The best we can do is to give some sort of numerical specification for it. If we're working in 45 dimensions, we've got to store the value function in 45 dimensions. If we have just 10 clicks in each grid direction, we've got 10 to the 45 numbers that we've got to store to get a very, very rough idea what the value function is. And you know, with 10 to the 45 numbers, we're probably filling everybody's hard drive in this room, if not in the whole of Brazil. So it's simply infeasible. Even if you could calculate this thing, you couldn't store it. And even if you could calculate it and store it, it might be quite a headache to do this. Well, it would be a headache to do this expectation. Right? So what we learned from thinking about this is that it's a very, very challenging question. So if we think of some examples, and most of the examples will be based on this little story where we're going to take, say, a Black-Scholes model, but we'll deal with some other examples later. So the log price is the volatility times the Brownian motion, and this can be in multiple dimensions. So the drift will be the riskless rate minus the variance, half the variance of the ith asset. Okay, so now we might say, well, what about a min-put? So this is a simple kind of derivative. So it just says that when we stop, we get the put value of the cheapest of the stocks at the time we choose to stop. So we get the best possible put value. Okay? So in this case, the state space would have to have the dimension of the vector of asset prices. So it might be 5, it might be 10, it could be 100. There's no limit to it. And similarly, we might think about, say, something like a fixed window lookback. So this time, the dimension of the underlying asset is just 1. It's a single Black-Scholes asset. But when we stop, what we're going to get is we're going to get the best value that took over the last week, 2 weeks, month, whatever the time window might be. So if we're thinking in discrete time, as we will be, the state variable now is the current log price, the previous log price, ... all the way back to the log price at time t minus a. So this is going to be an a plus one-dimensional vector, state vector. So if we were, for example, going to get the best price over the last month, well, we're talking about, what, 20 trading days, something like that. So that's already quite a high-dimensional problem. And it's not an unrealistic question to be asking. Okay? So let's make some observations about the general problem. If we're going to try and price a European option in 50 dimensions, the only way we can do that is by simulation. Right? We can't do an integration, one component after another. It's simply infeasible. So if that's true for European options, it has to be true for Bermudan or American options. This is the only feasible technology. It has to be simulation-based. We cannot have the value function. Right? We can't calculate it, we can't store it, and we can't access it. So we can't have the value function. So the value function, of course, would be enough for everything that we want, but what do we actually need? What do we need? What would constitute a solution to this problem? Well, it seems to me we need the following 3 things. At any time, we have to be able to decide whether we should stop or continue. At any time, we should be able to provide reasonably good bounds on what the value of the option should be. And finally, at any time, we would need to be able to provide an approximate hedging rule for the derivative that we've sold. Yeah? So the value function would be sufficient to give us all of these 3 things, but it's not necessary. And less may be enough, and the sort of the takeaway message of this talk is that actually simple approximations are often good enough to give you 1, 2, and 3. Okay? So how's it done? Well, this goes back to a paper of Barraquand and Martineau in 1995. I sort of rediscovered this myself earlier this year and then realized that these guys had done it a long time ago, but it's a very, very simple idea. So the Markov process that we're going to try and stop is completely generic. I'm going to describe a generic methodology, and all of the examples that we'll see later have been calculated off the same piece of code. It's the same piece of code generating all of the numbers. It's not, I mean, you have to change some of the inputs, you have to change some of the specifications, but there is a Markov process class that's part of the story. And the only thing that this Markov process class, the only method of this thing is step. It's simply, all you have to be able to do is to say, how do you simulate a step of this Markov process from a current position over a time interval of length t that you give it. So it's a completely generic setup. So the only thing we need is that, ability to simulate paths. Now, the stopping reward process is a function of t and xt. And if x is high dimensional and, say g was the min put payoff, now this is not going to be a Markov process. But the Barraquand Martineau trick is to say, well, let's pretend it is. Okay, so now we're looking at a supposedly Markovian one-dimensional process. It's real valued, and we're going to pretend that it's Markovian. Okay. Now, if it was genuinely Markovian and one-dimensional, it would be quite easy to solve the optimal stopping problem for that thing, because you just sort of put down a grid of points and approximate the process onto those grids, and then solve backwards using the dynamic programming equation. So we're going to try and do something broadly similar. And the idea here is that at each time we'll take a partition of the real line into intervals, and the ends of the intervals are denoted by a subscript t for the time and a superscript in brackets for the position. So you basically, at time t, you chop the interval, the real line up into some intervals, and then you're just going to observe which of these intervals the process falls into at that particular time. And if it falls into the bin k, then you set it a value eta kj. So it's going to be somewhere in that interval, and you assign a numerical value to that bin, and if the process falls into that bin, then it gets that value eta kj. And we'll just approximate z by this thing. So if the stopping value is in the kth bin, it gets the kth value. Okay, so this is now a pretend Markov process. It's discrete valued, it's discrete time. So what do we need to know? Well, we need to know what the kind of pretend transition function for this thing is, and that's very, very easy to do by simulation. So simulate ourselves a large number of these sample paths of the underlying Markov process, and what we do is, since we're pretending this is Markovian, we need an approximation to the transition probability. So what is the probability that we go from bin j at time t to bin k at time t plus 1? Well, what we're going to do is count all of the paths that go through bin j at time t and see what fraction of them then move on to bin k. Okay, so that's the obvious way to calculate the transition probabilities, or to estimate the transition probabilities. And that is literally all we do. And you can see that that recipe doesn't require any particular structure for the Markov process. It's completely generic. The only thing you need to be able to do is to simulate the paths. And that's why the Markov process class has only one method, and that method is the step method. Okay, well, let's carry on with this little thought experiment. So we've now got a sort of discrete time Markovian proxy, real-valued Markovian proxy, taking values in some finite set. And it's, of course, trivial to compute the value and the stopping rule for this thing, right? It's just, Bellman equation, and the matrix is, transition matrix might be 200 by 200 or 500 by 500, but it's basically trivial. So you can crank this thing out, and you can find the stopping rule. And the stopping rule would say that at time t, we would stop if and only if the stopping value, g of t and xt, was in the set, the stopping set, s tilde at time t. Now, of course, that's a stopping rule that you could go and use for the original process x. So I could simulate a path of x, and at each time I could check, is gt of xt in this set, which is just some union of intervals. I could check, is it in that set? And if it is, I stop, and if it's not, I continue. And you can evaluate that rule, which is an approximate, it's some sort of stopping rule. You could evaluate that rule by simulation. So if I want to know how good was that rule, I simulate 50,000 sample paths of x. On each one, I see what value I got according to that stopping rule. I average, then I know what the value of that thing is. Right. Well, now we've got no lights but air conditioning. Or maybe we've got no air conditioning and no lights. Well, it's okay. Oh, the air conditioning's come back on, but the lights haven't. Now the lights have come on. No worries. Yeah? No trouble. Yes. Okay, so this is a thing that we can do. I mean, we've made this gross assumption that this process g of txt is a Markov process. We've calculated the rule if that were indeed what it was, and then we see now by simulation what does that rule do for us. What value do we get? And this gives you a lower bound for the price of the option, because what you've done is you've applied a presumably suboptimal stopping rule. It's a stopping rule, but it's not the best. So the value is at least what you get from this procedure. And the stopping rule is incredibly simple. I mean, it's not like we have to kind of search for some oddly shaped space set in a 50-dimensional space. No, it's not. I mean, it's just a union of intervals on the real line. It's as simple as that. Okay, well, what about an upper bound for the price? I mean, Barraquand and Martineau, of course, were well aware when they published their paper that this gives a lower bound, and they remarked on two things. I mean, one was that it was in the cases where we had values that we could check, so where the price of the derivative was known by the means, the numerical values were remarkably close. So they noticed that. The other thing they noticed was that as you increase the dimension, the compute time just basically went up linearly with the dimension. Okay? So, there was no curse of dimensionality for this methodology. And you can see why that is, because the only place where dimension actually features in this story is in the dimension of the thing that you're simulating, right? You simulate a 50-dimensional process rather than a 3-dimensional process, but you're just taking a real valued function of that thing and then doing operations on that real valued function. So the only additional cost going from 3 dimensions to 50 is that the amount of simulation that you have to do has increased, but that's all. Okay, but what about an upper bound for the price? Well, their paper didn't offer any suggestions there, and this is sort of where I would think there's something a little bit added in what I'm talking about, and this is because subsequent to the 95 paper of Barraquand and Martineau, a few years later, people started to realize that you could actually get upper bounds for optimal stopping problems by this rather remarkable dual characterization of what the value of the optimal stopping problem was. So this is what we could traditionally think of. We think that the optimal stopping problem is to find the maximized expected value of the reward when we stop. But it turns out that this can also be seen, it is numerically the same as a minimum over zero mean martingales, martingale starting at 0, of the pathwise sup of G minus M. Fortunately, the lights on the projector haven't gone out. So, I mean, this is kind of surprising and unexpected, but at the time Barraquand and Martineau wrote their paper, this was unknown. And now what we're going to do here is we're going to use this characterization to obtain upper bounds, and then we're going to see how close the upper and lower bounds are in a range of examples. So this minimum is actually achieved. I mean, we can say exactly when this minimum is achieved. It's exactly obtained when M is the martingale of the Snell envelope process. And of course, this is, in general, not an easy thing to get hold of, but we do know what it is. And in the terms of the optimal stopping problem, the martingale of the Snell envelope process in this in this Markovian setting, is the martingale part of the value function v of t and xt. Okay, so this guy, if you think of this as a process indexed by time, this guy is a super martingale, and the provisible downward compensator of that thing is once you take it off, you get a martingale, and that martingale is the magic martingale, which gives equality here. Okay, so if we knew what the value function was, the optimal martingale difference sequence would simply be what is the value of the what is the value function next time minus what we thought it was going to be today, what we expected it would be today. So that would be the martingale difference sequence that would give us the perfect hedging martingale. Okay? But we don't know the value function v. However, we have got a proxy for it. We have this proxy value function v tilde based on this bogus assumption about one-dimensional Markovianity. So if we simply took that recipe up there and changed v to v tilde, then we would have a martingale. It wouldn't be the magic martingale, but it might be quite a good one, so that we could use this martingale to give us an upper bound. Okay? Right. So when we do this, when we try to calculate this, when we try to do this, we have to compute this expectation here, and there's really no kind of easy way, generic way to do this. I mean, the only thing I can think of is to just sort of do some sub-simulation. So we're running along some sample path. We've got to position xt, and we think, well, what's this expectation going to be? Then the only thing I can think of to do is to just fire off some single steps from xt. Where could it go? It goes to this place, to this place, to this place. Simulate a number of one-step moves using each of those one-step moves, I calculate this guy for the xt plus 1 that we achieve, and then average. And it's generally thought that, you know, simulations within simulations is a bad thing to do, that actually this is very expensive, it slows things down. It does slow things down, it's true, but since we're only searching like a one-dimensional space of values, and the time steps aren't very big, the moves aren't going to be very large, we don't have to be too delicate about it, right? And in most of the instances, I've just been using 25 subsimulations. Okay, so that's pretty quick. This is still the slowest part of the entire calculation, but it's not prohibitive in any sense. Okay? So, of course, now the question is how close are the upper and lower bounds? And that's going to depend on the problem that you're looking at. Well, let's take some examples. I'm going to just sort of walk you through a number of examples, and then we can, you know, see. Sometimes it works quite well, sometimes it doesn't. So let's look at the min put. And here's a table of values. And we're going to take independent assets. They all start at 100. The strike's 100, riskless rate 6%, half a year, and 60% vol. So there's a fairly good Monte Carlo price, which comes from another paper. But these high and low prices are the prices that we get by the methodology that I'm describing here. So the low price comes from pretending that the stopping reward process is a Markov process and doing the optimal stopping for that pretend Markov process. The high comes from the dual argument. And you can see that the gaps are, well, firstly, I mean, the low is below the true, is below the high, so that's reassuring. We don't have any violations of the natural inequalities. And the size of the gap it's 7% for two assets, but as you go down from 10, 15, 30, 60, it gets a lot smaller. There were no values for 30 and 60 in the original paper because it was just the methodology in use there was just far too slow to actually get that.
So Monte Carlo means Schwarz?
No, it means the method from my paper of 2002 or whenever it was. So you basically you guess sort of some hedging martingales. You make an optimal linear combination of these guys, and then you do a big simulation with those fixed weights. So it's a bit fiddly. I mean, you have to, you know, every single example you've got to sort of sit down and think about what would be good hedging martingales. So it's a very application-specific approach, whereas this is, as I say, is literally the same code for every example. And the runtimes, as you can see, are really quite manageable, right? I mean, it's going up, you know, roughly linearly. I mean, this is about twice that, and this one's about twice that, and so forth. So the runtimes, you know, this is a 60-dimensional state variable, and we're getting an answer that's good to less than 1% in just over a minute. Okay, this is a...
How do you explain that the gap is decreasing? Is it that the early assessed premium happens to vanish?
It's kind of the other way around. What's happening is that if you're taking the min of many assets, then this is, I mean, each one individually is a martingale, but the minimum is going down. So actually, as you get towards the end of this table, the best thing is simply to wait till capital T and then exercise. So I mean, this must be pretty close to the European value.
Yeah, that's it. It's a decrease of the early.
So it's a kind of a cheat. I mean, it's a kind of a cheat. This example is in a way too easy. And of course, when d equals 2, that's when it's most delicate, where the effect of the interaction and the sort of the downward drift is least pronounced, and that's where the error is biggest. Okay, well, let's look at a max call. So that's kind of the same thing, but turned round. When you have a call and you can sell the most expensive, or buy, sorry, the most expensive of the assets for K. And there's an example in a paper by Brody and Glassman 2004 where they worked through a number of these calculations. I think this was their stochastic mesh method paper, and they had 3-year expiry, it's not 0.2%. The volatility was 20%, so the volatility was 0.2. And they allowed 3 exercise opportunities, 6, 9, and so forth. And I mean, their method was you know, this is 5 dimensions, and their method, you know, they worked very hard, those guys, and they did a good job. And I think they were reasonably confident in reporting these accuracies in their outputs. So now we're going to use sort of like this very crude method. And what are we going to do? Well, again, we find that the bracket of low-high includes the true value, and the gaps are, you know, a few percent. I mean, there we got sort of 7.5%. Here we've got 6. Here we've got 3. So it's not too bad. And the run times, as you can see, are also quite manageable. I mean, 12 seconds at worst. Okay. Let's have a look at a basket put. Again, there's an example in the literature from a paper of Kovalov, Linetsky, and Markov, and they have a basket put on 2, 3, 4, 5, 6 assets. And again, we can use this methodology, and we're getting a gap of the order of 3 to 4%. Run times, this, for 12 assets, it's a bit slower. It's going up to nearly 100 seconds. But, you know, by the standards of this particular endeavor, that's not at all bad. Okay. Let's look at a fixed window look back. So this is where, when we exercise, we get the best price for the last 5 days, 10 days, 15 days, whatever it might be. And in this instance, we don't have existing numerics to fall back on. We don't have some comparison that we can refer to, but we can compute the low and high values according to this method. And as you can see, the gaps are still very, very small. I mean, this is like, you know, it's less than 1%. At worst, with a 25-day look back, that's looking at the best price over the last month. The upper and lower bounds are within 2.5% of each other. So it's pretty decent. And the run times are, you know, less than 2 minutes for those calculations. Well, it's a Monte Carlo method, so we can have any dynamics we please. So let's look at an example with stochastic volatility and stochastic interest. You know, there's a paper by, I think, 3 Finnish guys where they have a Heston stochastic volatility. Well, I don't like Heston stochastic volatility particularly. It's not a very good model for stochastic volatility. The only reason we actually do it is because we can calculate 1 or 2 things. I mean, the most important thing to remember about any of these diffusion models is that, you know, academics love them because we can calculate the price, you know, find out a closed form expression for the price of, you know, one derivative written on it, like the bond. It's easy to forget is actually you can't provide a closed form expression for virtually all of the derivatives you ever want. Anyway, so I've decided, well, simulating the Heston model is not very pleasant, and it's not a very realistic model, so I'm going to change it and just do something slightly different. And so I'm going to tell this little story, and you may dislike it, or you may not. You may think of some better version, and if you think of a better version, you can code it for yourselves. So there's going to be some sort of market Brownian motion, and we're going to have some log prices, D assets, and the log prices are going to revolve like, well, you know, there's a volatility out there which depends on time. The driving Brownian motion is partly the market Brownian motion and partly the idiosyncratic asset I Brownian motion. There's the appropriate risk-neutral drift, but the riskless rate itself is also stochastic. So we're going to have some sort of OU process for the stochastic vol. We're going to have some OU process for the riskless rate, and then we're going to express the individual volatilities as exponentials of this OU process xi, and the riskless rate as exponentials of this OU process z. So this is like, I mean, this is sort of like a Black-Kaczynski model, isn't it? You have an OU process for the log of the riskless rate, and for the volatility, you've got something rather similar. So, you know, you may not like those dynamics, but you can change them to anything you prefer. And then you can mess about with these things. So we have no comparison values, but, you know, we're getting gaps here where I think we're just varying the correlation. So the rho S there is the amount of correlation there is between the different stocks, assumed constant. I mean, you can't really do much else. And you can see that as you change from, you know, minus 15% to 0 to 15% to 30%, you can see that the overlap between this interval here and this interval here is basically gone. So as you increase this correlation, even though we're only getting bounds on the price, we're actually able to separate the different cases because the bounds are sufficiently small that we can differentiate between these different values of rho. And then we can choose a constant volatility, and we can vary the riskless rate, let the riskless rate vary, and so the initial value can be changed. And we see a similar sort of story there. And then we can do other things, constant R, varying sigma. We can let both R and sigma vary. It's just impossible really to kind of characterize exactly what's going to happen as you vary everything, but you can crank out a few instances and see what it looks like. Okay, so I think that illustrates that the methodology is quite wide-ranging and fairly flexible, but let me just sort of say a word about the accuracy, because of course when you're trying to price something, I mean, with Monte Carlo methods, if it was just, say, Monte Carlo valuation of a European option, you'd expect to get prices good to less than 1%. And if you want your price to be good to 1 part in 10 to the 3, you just crank up the number of simulations and keep going for longer. And this methodology is really only giving you values that are good to, let's say, 3%, 5%, 8%. It's nothing like that measure of accuracy. It's certainly not basis point accuracy, which seems to be like the yardstick that the industry would like to achieve. People want to have basis point accuracy. But let me just make a few observations. Okay. We've got errors from a variety of sources here. I mean, one is this Markovian assumption, this assumption that the stopping rewards a Markov process. We've got errors because we make discretizations of the stopping values into bins. We've got errors because of simulation. And 2 and 3 we can reduce. We can reduce the discretization error by having more bins. We can reduce the simulation error by having more simulations. But we can't get round number 1. I mean, 1 is intrinsic. I mean, that is a gross error, and there's just nothing we can do to reduce it. So we're stuck with it. But is this fatal? Well, let's think about it. What errors are coming from parameter uncertainty? So we plug into those calculations of the min put prices, we plug in a volatility of 20%. But is it really 20%? Maybe it was 19, maybe it was 21. Where did the 20% come from? Well, we went and looked at the squared returns over the last 3 months, and it looked like it was 20% vol. But if we used the squared returns over the last 6 months or the last 1 month, it might have been 19, it might have been 21. Are we sure that this option volatility is going to remain constant at 20% all the way through the lifetime of this option? We're not. So, uncertainty of the order of, say, 19 to 21% in this supposed 20% volatility would be perfectly normal. So what happens to this method if you run the calculations pretending the volatility is 19% or 20 or 21? Well, look at the range of values that you get. 2.98 to 3.07, 313 to 325, 328 to 342, 261 to 272, 275 to 287, 293 to 304. There's no overlap. Right? So the accuracy with which this method is pricing the derivative is comparable with the sort of errors that you've got in the inputs. So to me, this is a workable solution to the problem. I mean, we're not going to get basis point accuracy, but the sorts of errors that we're getting are comparable to the sorts of errors that are out there in the input data. And why does the industry want basis point accuracy?
Because of the competition, yeah.
Well, I don't know. It seems to me that, I would have said the reason you want basis point accuracy, you want high accuracy, let's say, is you want to think about a delta hedging rule, that you want to sort of change the price of the underlying by 1%, and you want to have a sort of 1% error at most in the hedge that you're supposed to put on, the delta hedge you're supposed to put on. That's why you want basis point accuracy. But the thing is, the dual martingale that you generate by this process is the hedge. You don't need to do delta hedging. You do not need the price accurate to a basis point to calculate a delta hedge, because the method is telling you the hedge anyway. Right? So actually you don't need basis point accuracy to get the hedging. The hedging just comes from the method. Okay, so I've shown you some examples where it works well. Let me show you one where it doesn't work very well. And this is the fixed strike Bermudan-Asian option. And here the payoff is not the stock minus the strike, but the average price of the stock minus the strike. Okay, so you average the price over, well, not just from 0 up to T, you add on a little sort of burn-in window prior to the start of the option, otherwise you just get this, this thing sort of can fluctuate wildly at the early times. So you have a little sort of burn-in window of length delta, and in the calculations that follow, there's a sort of initial lockout time. You're not allowed to exercise this thing for 3 months or something. Now, if we notice that the payoff of this guy, e to the minus rt times at minus k, is actually differentiable with this derivative, then we know that we would never exercise when this was positive, okay? Because it just means that if we're in the money and this thing is rising, then there's no sense in exercising. You should wait because it's going to go up. However, a rule that simply looks at the value of AT isn't going to be able to tell you that. So any rule that is based solely on what AT currently is must fail to capture that feature and probably isn't going to do very well. And indeed, this is what we find. So we've got some prices from the Longstaff-Schwartz paper for calculated by finite difference, and the gaps now are, sometimes not too bad. There's 4%, less than 5%, but there's some bad ones in here. Look, 18%, 14%. These are not good numbers. I mean, we would like it to be a lot better than that, and it's really bad. Okay, so the method doesn't always work. If we compare that with a floating strike Bermudan-Asian, where now you get A minus the current stock price, the story looks very, very different. That the gap is just a few percent, and it's basically it's because you can divide through by S, use S as the numeraire, and then A over S is a kind of sensible sort of thing. Okay, well, I guess I'll wrap up at this point. So what I've described is a generic methodology for handling Bermudan options. The only thing that we require about the Markov process is that we can simulate it. That's it. The computational cost is largely insensitive to dimension, and by that I simply mean that it's roughly proportional to dimension, because the cost of simulation is the only thing that's affected by dimension, and that goes up linearly with dimension. The gap between the upper and lower bounds is, usually in the range sort of 5 to 8%, sometimes less. Sometimes it's a couple of percent, sometimes it's 9 or 10. I mean, in bad cases, it's a lot more than that. It's 15, 18. But the kinds of gaps we're getting are comparable to the errors that you would get from the input parameters. The stopping and hedging rules obtained are very simple. It's very, very easy to describe what the stopping rule should be. You just look at what is the stopping value now. Is it in this union of intervals or not? The hedging rule is defined in terms of the martingale you get from the value function. The computational times are, well, I mean, rarely more than 10 to 20 seconds. Okay, sometimes they go up to a couple of minutes or so, but it's not like we're sort of having to sit there for half an afternoon for the numbers to come back. It's you can run it in a few minutes at worst. There we are. That's all I had to say. Thank you.
Thank you very much.